In this video, we'll talk through the notes for section 3.1 called the Fourier Method. This is a method developed by Fourier in the late 17 or early 1800s to solve differential equations like the heat equation. So we start with this equation, which is the heat equation, but it's on a bounded domain. So we're imagining in this scenario that we have a heated metal rod where the temperature at the endpoints is held constant at 0. So the endpoints are at x equals 0 and x equals L. So L stands for the length of the rod. The initial temperature at each point is given by this function f, and that gives us the initial conditions. For simplicity, we will let L be equal to pi and k be equal to 1, where k is the constant in the differential equation. So the initial boundary value problem becomes what you see here. The partial derivative of u with respect to t is equal to the second partial derivative of u with respect to x. And furthermore, we have u at 0, t is equal to 0 for all t, and u at pi, 0 is equal to 0 for all t. That should actually be a t there. That should be a t. So we're imagining that for all time, at the endpoints, the temperature is held a constant 0. And again, our initial temperature at each point is given by this function f for x in the domain. This is a bounded domain. We're imagining that the length of the rod is pi units, and we chose pi just to make the computations a little simpler later on, as you'll see. To solve this equation, we will make an assumption on the nature of the solution. We're going to assume that the solution u is a product of a function of x times a function of t. This method of solving initial bounded value problems is known as the method of separation of variables. It's a method that we'll see again in more detail later. For right now, we're just going to give it a try and see what happens. So how does this assumption affect the problem? Let's look at the differential equation, which you see here. U sub t equals u sub xx. So on the left, we have the partial derivative of the product with respect to t. And on the right, we have the second partial derivative of the product with respect to x. Since this is a product of a function of x times a function of t, we don't have to use the product rule here. So we just compute directly, taking out the constant function. Well, it's constant with respect to t on the left. So this function of x is constant with respect to t, so it just comes out of the derivative. So you're multiplying by t prime. Capital T is a function of only one variable, so that means that it's just an ordinary derivative. It's not a partial derivative. On the right, we have the same sort of thing. This function of t has no x's in it, so it's constant with respect to x, so we can just factor it out. On the other hand, this function of x is a function of just the variable x, so the second partial derivative with respect to x becomes x prime prime. So now we have an equation in terms of ordinary derivatives. The nice thing about this is we can separate it, hence the name. We can separate it into an equation, or rather two equations, each one in terms of only one variable. And it comes from this basic fact that if you have this function capital X times capital T prime, and that's equal to capital X prime prime times capital T, the first thing we do is we divide this T over to the other side. So we divide that over here, like so, and then we divide this function capital X over to the other side. So we divide by capital X and put that over here. And we're dividing by this t of t. So what happens is you end up with this equation here. So this equation tells you that the ratio of t prime to t is equal to the ratio of x double prime to x. Now, why is this so useful? the ratio must be constant. Now, why is that? Well, let me just write down that this ratio must be equal to a constant. So why is that? We have a function of t on the left side and a function of x on the right side, and we're saying that they're always equal. The only way that could possibly happen is if both functions are constant. You can think of it this way. If we imagine this function of t on the left, we can let t vary, but it has to be equal to this function on the right for all x. So imagine holding x constant. You hold x constant, and then there's just one value on the right. So if x is held constant, that's just one number. And then on the left, we allow the t to vary. That means even though the t is varying, the ratio has to remain constant. Similarly, if we hold t constant while we vary x, then we have that the ratio of these x terms, x prime prime over x, must be equal to the constant on the left. So that tells us that the ratio on the right must be a constant as well. So it's customary to let that constant be equal to minus lambda. This is known as the separation constant. Now, the fact that there's a minus here is just customary for notational purpose later on. So we just let this be equal minus lambda. At this point, there's no statement about whether lambda is positive or negative. We're not saying that this constant, we're not saying that the ratio t prime to t, which is equal to the ratio of x double prime to x, we're not saying that that's a negative number. It's entirely possible that lambda might be negative. We'll find out depending on the problem. Okay, so our PDE has now become two ODEs, which we see here. So if you multiply this capital T over to the other side, you have t prime is equal to minus lambda times t, which you can then add. So our first ODE is just a first order linear homogeneous differential equation. T prime plus lambda t equals 0. In our second one, we do the same thing. We multiply the x over to the other side, and then we add it. So we have x double prime plus lambda x is equal to 0. This is a second order linear homogeneous ordinary differential equation. Okay, so what are we going to do with these? We're going to solve them. Now, we're not solving them without any extra conditions. We know that there are certain conditions along the boundary. So what do those boundary conditions tell us about t or x or anything to do with this problem? That's something we need to work out. So let's remind ourselves what the boundary conditions are. The boundary conditions tell us that the temperature is a constant 0 at all time on the boundary. So u at 0, t is equal to 0 for all t, and u at pi, t is equal to 0 for all t. But u at 0, t is equal to x0 times t, capital T at lowercase t. And u at pi, t is capital X at pi multiplied by capital T at lowercase t. Now each one of these is equal to 0. Each one of these products is equal to 0 for all t. Now in order for that to be true, it needs to be true that one of these constants, or one of these factors must be 0 at all times. Now it's possible that t at lowercase t, it's possible that that's 0. But if capital T at lowercase t is 0 for all t, that tells us that our function u, which is the product of these things, is 0 at all times. We don't want u to be 0, that's the trivial solution. And it might not even be accurate as long as this function f is not 0. So if this function f is not always 0, then it certainly can't be the case that u at x, t is always 0. So we'll assume that t at t, capital T at lowercase t, we'll assume that that's not 0 for all t. Now the consequence of that, since we know that this product, x at 0 times capital T at lowercase t, since we know that this product is equal to 0 for all t, it must be the case that x at 0 is equal to 0. Similarly, we want to assume that capital T at lowercase t is non-zero, or at least it's not always 0, but the product is always 0. So the only way that can happen is if x at pi is equal to 0. So this gives us a boundary condition, or a two-point boundary condition, for our x differential equation, x prime prime plus lambda x equals 0. So let's just write it out here. So we have a two-point boundary value problem. Up at the top I just made that comment: if t at t is equal to 0 for all t, then u has to be equal to 0 for all x comma t, which is not something that we want. Unless, of course, our initial condition tells us that f is always equal to 0. But we're going to assume not, just to make the problem a little bit less trivial. So we have a two-point boundary value problem in x. Capital X prime prime plus lambda times capital X is equal to 0, where we have that x at 0 is 0 and x at pi is 0. So this is a second order ODE, so let's go ahead and solve it. So the characteristic equation is r squared plus lambda is equal to 0. So the nature of the solution depends on the sign of lambda. So let's divide this up into three cases. So the first case is when lambda is negative. So if lambda is negative, then let's write it as lambda is equal to minus mu squared, where mu is some positive number. Mu squared is necessarily positive, so if you put a minus sign in front of it, something's necessarily negative. So since lambda is less than 0, we're just writing lambda as equal to the opposite of some positive number, some necessarily positive number. Now, why are we writing it as mu squared instead of mu? It's just for computational convenience, as you'll see, because that tells us that the characteristic equation is r squared minus mu squared equals 0. So solving for r, we get that r is equal to plus or minus mu. So that makes it very easy for us to write out the general solution, which is capital X is equal to c1 times e to the mu x plus c2 times e to the minus mu x, where c1 and c2 are constants. Now we check the boundary conditions, and this is where things get interesting, because if you check x at the first boundary, when little x is equal to 0, let me just fix that. When little x is equal to 0, what happens? Well, the exponentials just go away because it's e to the 0 in both cases. So you just end up with c1 plus c2 is equal to 0. So c2 is the opposite of c1. The other boundary condition tells us that capital X evaluated at pi is 0. So if you just plug in mu is equal to pi, you end up with this expression. But of course we know that c1 is equal to minus c2. So, or the way I've written it is actually c2 is equal to the opposite of c1. So we just take that c2 and we replace it with minus c1, or the opposite of c1. Let me just fix my handwriting. c1, and that's what we have here. So then we can factor out the c1. Now we don't want c1 to be 0, because if c1 is equal to 0, then we have a trivial solution, and we've already decided we don't want trivial solutions. So we're going to assume that c1 is not equal to 0. So in particular, that means we can divide by it. So you divide everything by c1, and of course there's no 0 over c1 is still 0. Then you just have this statement. Well, you have e to the pi mu is equal to e to the minus pi mu. Of course, the exponential is a one-to-one function. The only way that can happen is if their exponents are the same, which means that pi mu is equal to minus pi mu, or mu is equal to minus mu. The only way that can happen is if mu is equal to 0. But it can't be, because mu is assumed to be positive. If mu is equal to 0, then lambda is 0, which contradicts the fact that lambda is a negative number. So that means that this possibility is not a possibility, it's a non-possibility. Okay, so lambda can't be negative. Can it be 0? If lambda is equal to 0, then the characteristic equation is r squared is equal to 0. So what does that mean? That means that the solutions, the homogeneous solutions, are e to the 0x, or x times e to the 0x. But e to the 0x, of course, e to the 0x is equal to 1. So that means our general solution looks like that. It's c1 plus c2x. So is this possible? Well, the boundary conditions will quickly show you that the only way that this can happen is if c1 is equal to 0 and c2 is equal to 0. So the only solution is the trivial one. But again, that implies that the solution to the partial differential equation, that implies that u is constantly equal to 0. And that's something that we're avoiding. So that tells us that this case is also not possible. So the only possibility is that lambda is greater than 0. Let's try that out and see if we get something which is not impossible. It might be that there's just no solution to this problem, but let's find out. So let's follow our lead from the previous case, or from the first case. Assume that lambda is equal to mu squared, where mu is some positive number. And again, we're just writing it as mu squared because that helps with the arithmetic. So the characteristic equation is r squared equals minus mu squared. So that means r is plus or minus I times mu. It's purely imaginary. So the general solution is given in terms of cosines and sines. So capital X at lowercase x is equal to c1 times cosine mu x plus c2 times sine of mu x. So let's see if this is possible. What do the boundary conditions say here? Capital X at 0 is c1 times cosine of 0 plus c2 times sine of 0. But sine of 0, of course, is 0. And cosine of 0, of course, is 1. So we end up with c1 times 1 plus c2 times 0, which is just c1. So already we have that c1 is equal to 0. So the question is, can we ensure that c2 is not 0? If c2 is not 0, then that means the only possible solution is the trivial solution. So let's try the other boundary condition, which is capital X at pi. So that's c1 times cosine of mu times pi, but we've already established that c1 is equal to 0, so this term is not even there. Plus c2 times sine of mu pi, which we have here. Now we want that to be equal to 0. Now of course it's also possible that c2 is equal to 0 and then you have the trivial solution. But let's assume that c2 is not 0 because we want a non-trivial solution if we can find one. So we need the other factor to be equal to 0. So is it possible for sine of mu times pi to equal 0? And the answer is yes, of course it is. As long as mu is an integer, this will be equal to 0. Sine of mu times pi is 0. Now, we're assuming that mu is a positive number. We wrote that down somewhere, right here. Mu is assumed to be a positive number. So that means as long as mu is a natural number or a positive integer, sine of mu times pi is equal to 0. So these are the possible values for mu right there. So what does that tell us for the possible values of lambda? Well, lambda is equal to mu squared. So in other words, we're going to have a different choice of lambda for every n. So we call it lambda sub n. So we have lambda n is equal to n squared for each n in n. So we have choices of lambda that will make this non-trivial. The corresponding x function, capital X, is given by lambda n at x is equal to sine of nx. Because, of course, capital X is this expression right here. And we know that c1 is equal to 0, so that term goes away. So we just have some constant times sine of lambda x, but lambda is n. So for each, or for mu rather, mu is n. So let me just rewrite that. So this term goes away, and so capital X is just this term, where mu is equal to n. So capital X at lowercase x is equal to c2 times sine of mu x, but, well, let's just write it mu x, where mu is some natural number. So those are our solutions. So of course c2 is just an arbitrary non-zero constant, so the corresponding function we can just write as xn at x is equal to sine of xn. So we call xn an eigenfunction, and we call lambda n an eigenvalue. These are terms taken from linear algebra, and it comes from the fact that if you have this relationship, so our relationship here is capital X prime prime plus lambda n xn is equal to 0. So if you just subtract this to the other side, minus lambda n xn, and subtract that from over here as well, capital X n, you end up with an expression that looks like that. So on the left we have a differential operator. So if we write that capital L at capital X is equal to x prime prime, then this equation is capital L at x is equal to minus lambda n times x. So it looks like from the kind of equation that you get in matrix theory that leads you to an eigenvalue for an eigenvector. Of course, there's this minus sign in front of it, but we just call lambda n the eigenvalue, and we don't call x an eigenvector because it's a function, so we call it an eigenfunction instead. Okay, so we now want to do the same thing for t. So in this case, the ODE is t prime plus lambda t. T prime plus lambda t. Now, of course, it will depend on lambda, and we have lots of different lambdas now. We're calling them lambda sub n, but we have all of these different lambdas right there. So we have a different equation for every lambda n. So the viable values for lambda, as I just mentioned, are lambda n equals n squared, so our equation becomes this. T prime plus n squared t is equal to 0. This is a first-order ordinary differential equation. It's linear, it's homogeneous, so we can solve it in the usual using the usual ODE methods. And this one's straightforward enough because you just have that t prime is equal to some constant times its own derivative. And so it's necessarily the case that capital T is equal to e to the minus n squared t, where minus n squared is that constant. You can, of course, solve this equation using separation of variables. So the idea is that you have t prime over t equals minus n squared. So then you integrate both sides and you get ln of the absolute value of t is equal to minus n squared t, and then you exponentiate both sides. So then you'll end up with t is equal to plus or minus some constant times e to the minus n squared t. And this is some arbitrary constant, but we're going to ignore the arbitrary constants for the time being. We'll introduce them later, so we'll just write t at t equals e to the minus n squared t. Of course, any constant would work unless you had an initial condition. But so for each n in n, we have a function x sub n equals sine n of x, and t sub n equals e to the minus n squared t. So a solution to the initial value boundary problem is given by this u sub n right here. So that's just the product of this xn with this tn. So that product gives us a solution to the initial value boundary problem. So in fact, that's true for every n. For every n, we have a solution that looks like that. And of course, you could put an arbitrary constant in front. So un equals some constant an sine nx times e to the minus n squared t, where that's our arbitrary constant. So of course, we should have an arbitrary constant in front of this sine term there. There should be an arbitrary constant there, and there should also be an arbitrary constant here. But instead of worrying about those, we just multiply them together, so to speak, and that gives us our arbitrary constant there, because we're not really solving the differential equation for x or the differential equation for t. We're interested in the heat equation. So we're going to put these together by multiplying the two individual solutions, x at n times t at n, and we can put the arbitrary constant in front of that. Now, but that's a solution to the initial value boundary problem actually, sorry, this should be, I knew something didn't sound right. Initial boundary value problem. Okay, sorry. So this is a solution to the initial boundary value problem for every n. So this gives us a solution for every n. So we claim that the general solution is obtained by adding all of these things together. Now, this is true. It's true that this is a solution for finite sums, but now we have an infinite sum, so it's not really clear. We have issues of convergence that we have to deal with. Do we even know that this series converges? In a formal way, if you just assume that the series converges, and you assume that it converges in such a way that we can differentiate term by term, then you can show that this is indeed a solution to the initial boundary value problem. But that's assuming various things about convergence. It's assuming that the series does converge. It's assuming that it converges in such a way that you can differentiate term by term. So we'll just assume for now, or we'll take for granted that that's true, that it converges, but converges nicely in some way that allows us to do term by term differentiation. We'll investigate those questions shortly, but for right now we'll just take it for granted. So we have an initial condition, which is that u at x comma 0 is equal to f at x. So that tells us how to find the constants a sub n, well, in a roundabout way. We know that u at x comma 0 is equal to f at x, but we can also just plug in t equals 0 into this solution to see what happens. Well, if t is equal to 0, then we put a 0 right there. So then you have e to the 0, and that term just goes away. E to the 0 is 1. So then you're left simply with a at n, the a at n term right there, times sine of nx, which is right there. So the initial condition tells us that f at x is equal to this infinite sine series. So the question is there any way to determine the value of a sub n from this information? And it turns out that there is. So we have a theorem, and the theorem says that if f is equal to this infinite sine series, the sum n equals 1 to infinity of an sine nx, then you can solve for the coefficient a sub k by evaluating this integral. So it's 2 over n times the integral from 0 to pi of f at x times sine of kx dx. So if you take f, and you multiply it by sine of kx and integrate it from 0 to pi, you're going to pick off the kth coefficient. There will be this extra factor of pi over 2, so that's why you just have to, well, you'll get an extra factor of pi over 2, so you have to multiply by 2 over pi. Okay, so how do we show that this is true? And we can show that it's true. So it all rests basically on this equation right here, or this equality right here. So if k is a natural number, then we can show that the integral from 0 to pi of sine nx times sine of kx is equal to 0 if n is not equal to k, and pi over 2, that factor of pi over 2 that I was talking about earlier, if n is equal to k. It's that factor of pi over 2 that means you have to multiply by 2 over pi. So this is easy enough to show just using trig identities and integrating. So if n is not equal to k, then sine of nx times sine of kx, just using a trig identity, is equal to this. And these terms we can integrate individually to get these. So this is why we want n not equal to k, because you're dividing by 0 here, if n is equal to k. And if you evaluate this, when sine is equal to pi, these two go away. When sine is equal to 0, these go away. So you just end up with 0. So it's easy enough to show. If n is equal to k, then you still have the same formula, but you just end up with, if n is equal to k, you just end up with a 0 here, so then you have cosine 0 is 1. Otherwise, you double up, so you have cosine of 2nx. This is the double angle formula, or the half angle formula, depending on how you write it down. So we have sine of nx quantity squared is 1/2 times 1 minus cosine 2nx. And this is easy enough to integrate, but you don't end up with 0, you end up with pi over 2 because of this term. So you have this 1/2 from the trig identity right there, and then this term is what gives you the pi at the boundary. So you have pi over 2. So this system of functions is what we call an orthogonal set, or an orthogonal system, because if you integrate, well, there should be a dx there. There should be a dx right here. If you integrate their product, you'll get 0 if the n and the k are different. If the n and the k are different, you'll get 0, but they're non-zero if they're the same, if n is equal to k. If you multiply by the constant square root of 2 over n, then you get what we call an orthonormal set, because their integrals will either be 0 or 1. We'll talk more about this in a future lecture. So we can use this orthogonality property to compute a sub k. And basically we just integrate this f at x against this sine of kx, and we're going to take it for granted that we can integrate term by term. So we have, that's f right here. This was our assumption on f. So what we're going to do is we're going to integrate term by term, which means we're going to take this integral symbol and we're going to put it inside here. Now the an is constant, so we can just take that out of the integral. And then we have this sine nx times sine of kx, and we know that that's 0 if n is not equal to k. So it just reduces to one term when n is equal to k, and so that gives you this a sub k times the value of that integral, which is pi over 2. So if you want to solve for ak, just divide this integral, just divide that integral by 2 over pi, and you get this formula right there. Now we integrated term by term, which is something that needs to be justified, but assuming that this is possible, we've solved the initial boundary value problem, and this is our solution. U at x comma t is equal to the sum n equals 1 to infinity of an, where an is given by this formula, times e to the minus n squared t times sine of nx. Now this formula for ak, that formula for a sub k, that was given to you by the initial condition. So just like a usual differential or a usual initial value problem, you end up with an arbitrary constant, and in order to determine the value of that arbitrary constant, you need to use the initial condition. The only difference here is that we have infinitely many of these a sub k's. We have an a sub k for every natural number k. So we have to find infinitely many of these, but we have an entire function to do that with, so to speak. F is defined for all x. So we can use this formula to actually compute those a sub k's. Now, some of this, as I said, needs to be justified. At the time that Joseph Fourier came up with this method, these steps were not yet justified. So the solution worked, but it seemed to be a little bit dubious because we didn't understand, or I should say they didn't properly understand issues of convergence. And indeed, much of the development of analysis around this time was owed to trying to understand what this solution really meant. And we'll talk about some of those issues in a future lecture.